Hello everyone, it's Chris Marrows here. I'm recording this talk at the end of June 2021. At the moment I'm not sure whether I'll be able to travel to Sicily or not. I hope it's possible, but it may actually turn out not to be. Nevertheless, I'm really pleased to thank Giovanni and all the team for putting this conference together and giving me the opportunity to present our work on Skyrmions over the last few years. So let's get started. Okay, so the title of the talk is Skyrmions in Chiral magnetic multilayers. Okay, so let me very quickly, before we get started, just acknowledge the people who've done the work, particularly in Leeds. It's Katerina Zeisler, who worked in the Magic Sky Consortium, alongside Simone Finizio at the Palshare Institute, who together did a huge amount of work on Skyrmions in multilayers. More recently, Elwar Haltz and Chris Barker have been a postdoc and PhD student at Leeds, have been working on synthetic antiferromagnets, but as you can see, lots of other people have helped in various different ways, and all these logos at the bottom show the different organizations that have paid for work you're about to see. So very briefly, just to introduce magnetic skyrmions, this is Tony Skyrm down here. He came up with the kind of mathematical concept of a topological defect in a field that was stabilized by its topology and had sort of particle-like properties. He was working in high energy physics. I think it's fair to say the idea didn't really catch on there, but it did in condensed matter physics, and particularly in magnetism. And a magnetic skyrmion looks like this sort of famous diagram here. And so we can see, in this case, it's circular. It has a downward pointing moment at its center. It has upward pointing moments all around the rim, and so that means it can be embedded in a uniformly magnetized background. And then the spins in this case kind of swirl around the center. And the important thing is that wherever you look, or you can find somewhere in this structure a spin pointing in any direction in space. So it completely wraps that spin sphere, and that means it's topologically distinct from a uniform state or any other equivalent trivial state. Mathematically, if we evaluate this expression over the whole of the 2D skyrmion structure, this will return a value of 1, which corresponds to a wrapping of the sphere, whereas a uniform magnetization would give you 0. So this is the so-called winding number, which characterizes the topology. I'll come back to that in a moment. So these things have particle-like properties. For instance, they can crystallize. And this is a Lorentz micrograph, one of the very first direct images of magnetic skyrmions from Shisheng at Riken. And then there are some interesting emergent electrodynamics that arise from this topology. And that requires the idea of a Berry phase. So this is Sir Michael Berry over here. And again, in this famous diagram, we have the spin adiabatically tracking the magnetization as the electron passes through the skyrmion, picks up Berry phase. We can treat that as a Haranoff-Bohm phase, which gives us a fictitious magnetic flux. The flux is sort of mathematically fictitious, but the Lorentz force is somehow real, and we do in fact get a deflection of the electrons that we can measure as a contribution to the Hall effect. So just to dwell for a moment on the idea of topology, one of the important features of topology is that it is really just counting and counting integers. So, you know, here we have what I would call a bread roll, and that has no holes in it. So that would be 0. Here we've got a bagel, that's got 1 hole in it. I don't have such a sweet tooth, so I prefer a bagel to a donut. But that has a single hole. So that can be 1. And here's a special kind of Swedish pretzel that only has 2 holes in it. And so that kind of corresponds to 2. You can imagine sort of carrying on here.
So the important thing is that these are discrete jumps. You can't have kind of half a hole in something. There isn't, you can't have something that corresponds to a half in this case. So, you know, 1 would be 1 skyrmion in our material, 2 would be 2, 0 would be uniform magnetization. But you can't have kind of half of something. Everything is quantized. And I can just sort of illustrate the stability of the skyrmion a little bit by making an analogy with this Möbius strip. So if we have a simple loop of paper, then we would have 0 twisting. And so in fact, you can define a winding number here in 1D as you go around the loop. So here you get 0. Here's the Möbius strip, has a turn in it, a single twist, so that would correspond to 1. And again, you have to have sort of you know, an integer number of twists so that you can rejoin the paper. And importantly as well, then the topology is sort of stabilized in this structure, and you can treat it quite roughly. You know, you could imagine scrunching these things up, rolling them into a ball, you know, spreading them out again, and you could come back and look after doing all that whether you had a 0 or a 1 state. And so storing data in topology means it's intrinsically quite stable, and that it makes skyrmions one of the reasons why skyrmions are being looked at the moment for data storage. Okay, so these are our multi-layers that we've studied skyrmions in. They look like this. They have very thin layers of cobalt, sub-nanometer thickness, with platinum and iridium above and below. And those different heavy metals give us a Dzyaloshinski-Maria interaction, which makes the magnetism chiral and stabilizes the skyrmion. They're magnetized out of the plane. Here are some polar Kerr loops to show that. And these are some Lorentz micrographs where we've added some false color, red and blue, to indicate whether the magnetization is in or out of the plane. And you can see these sort of dendritic domains that shrink or expand with field, but you can also see some little isolated structures. So these were sort of our very first attempts to see what we could find. And you can find these kind of little tiny circular things. In this case, the smallest one is about 150 nanometers across, which has the skyrmion topology. So that is a magnetic skyrmion in this multi-layer structure. Of course, lots of other groups have found the skyrmions in these room temperature materials. This is a far from exhaustive list. In fact, actually, you can see that these are sort of some of the first observations, and there have been many, many more since. So apologies if your favorite paper's been missed out. But you can see all the samples have a similar structure. There's a thin magnetic layer. It's got different materials above and below it. One of those materials is a heavy metal to provide DMI. And you can have a single tri-layer. And in this case, you know, we've got skyrmions ranging from sort of micron scale down to tens of nanometers. Or you can build up those tri-layers in many repeats into multi-layers. And again, you know, we've got skyrmions that are on the scale of tens or a few hundred nanometers. Different materials. As I said, skyrmions, the topology makes them stable. We've just seen that they can be very small. And they also respond quite well to currents and spin torques for manipulation. And so there is the idea that they could be useful for different kinds of spintronics, maybe like a racetrack memory. We could connect racetracks to do logic, or this is a proposal, this has been realized actually experimentally, for a sort of chamber where skyrmions can diffuse around and help generate some randomness for probabilistic computing. So whatever you want to do, and I'm not sure the skyrmion racetrack is enormously useful compared to a domain wall one, but it is a nice framework for thinking about what you would have to do to build any sort of skyrmion device. You need to be able to write skyrmions, write data by nucleating skyrmions. You need to be able to manipulate that data by moving skyrmions around. And you need to be able to read your data back by detecting the skyrmions. And you'd really like to do all that by electrical means. So in this talk, I'll show you that we've managed to achieve all those three things.
Okay, so let's take a look first of all at the nucleation, how to create a skyrmion. So this is the structure that we used to nucleate our skyrmions. So the magnetic part is this rectangular wire. In the middle here, it's 2 microns wide, and it's got copper contacts at the top and bottom so that we can pass current pulses through it. And you can see that this contact is shaped into a finger. There's a radius of curvature of about 250 nanometers at the tip there to generate a large and divergent current density at that point. And then separated from, electrically isolated from the wire, is this copper omega coil, which we can use to generate fields around this injection point in order to reset a uniform magnetized state. And this whole thing has been fabricated on a silicon nitride membrane so that it can go into the Stixum at Swiss light source, and we can image what happens when current pulses go through it. And what happens is this. So here are 3 XMCD Stixum images. First of all, we have a uniformly magnetized wire, and then a current pulse has been injected and generates this little region of dark contrast here, which is the skyrmion, and then we can use the coil to apply a field and delete the skyrmion. And by doing a series of experiments like this, we're able to build up this kind of phase diagram. So this is the duration of the current pulse, and this is the current density of the current pulse once it's inside the wire. So you can see all down here where the current pulse is too short or too weak, basically nothing happens. And up here where the current pulse is too long or too intense, we generate some complicated domain structure, which is probably due to overheating the wire. But there's a band across the middle where we generate a single skyrmion at the tip of the injector, and it's very deterministic. You get exactly 1 skyrmion every time for each current pulse, and this is all done at 0 field, by the way. And the size of the skyrmion, you can see, is a little bit smaller on this side of the band, a little bit larger on this side. So this thing is it's a bit like a bubble or a balloon. It's sort of inflated by the current pulse and then stops and remains stable at that size. Moving on to the propagation of skyrmions. Again, we've got 2 micron wide wires, but these are a bit simpler. They just have flat contacts at either end, but it's a very similar multi-layer stack, actually using cobalt boron as we did for the nucleation. These experiments, in fact, were done before we knew how to make the nucleators work, which is why we don't have them. But the data were a little bit more tricky to analyze, and so it took us some time to understand what was going on. Anyway, again, these wires are fabricated on membranes that we can look at them in the Stixum, and you can see here Stixum images of different magnetic states at various different fields. So these skyrmions are injected or created just by some sort of thermal process. We inject a couple of current pulses in the range where the wire is heated up enough that when it cools down, it's populated with skyrmions. So that's in the mid 10 to the 12 range. But then with current pulses about 10 times weaker, something like in the mid 10 to the 11 range, there's much less heating, but we can move the skyrmions and they gradually kind of drift along the wire in response to a series of these pulses. So we would take an image after every 2 pulses and see what had happened. So these coloured dots represent single skyrmions where we've tracked the motion, and you can see that they tend to move down the wire in the direction of the conventional current, which shows that it's a spin-orbit torque that's causing them to move. But they also tend to drift a little bit to the side, and that sideways motion is referred to as the Skyrmion Hall effect, which we'll come back to in a minute. So we did this kind of experiment at various different values of field, and this negative field is intended to squeeze the skyrmions and make them a little bit smaller. And that's because the sort of simple Taylor theory predicts that there should be a diameter dependence to the angle at which these skyrmions move. So we wanted to look for that. So this is this Skyrmion Hall effect. It's often compared to the Magnus force. If we have a spinning ball, then it will experience, it's not only the force with which you kicked it, but there's a Magnus force, and that Magnus force tends to make the motion of the ball curve as it moves through the air, because it's displacing the air to one side. So similarly with our skyrmion, because it's a chiral object, it experiences not only this drive force from the spin orbit torque that is sort of pushing it in the current direction, but also this transverse force that has some sort of analogy with this Magnus force. And so the skyrmion will move in this direction at some angle to the drive, and that angle is referred to as the Skyrmion Hall angle. So that's what we've plotted here. Here, for all of our skyrmions at every field, in this case as a function of the diameter of the skyrmion. So we get this big cloud of points. And if we take a look at this, what we can see is the sort of center of mass of this cloud is a little bit above 0 degrees, actually about 9 degrees. And that doesn't seem to have very much dependence on the diameter of the skyrmion. On the other hand, if we plot the same set of Skyrmion Hall angles against the velocity, at which that skyrmion is moving, then of course we still have the same average 9-degree angle. What you can see is that the spread varies quite a bit. So over here, where we have some fast-moving skyrmions around 10 meters per second, they move with Skyrmion Hall angle not far from that 9 degrees, which is actually roughly what you would expect sort of intrinsically on the basis of a Taylor type model. On the other hand, here we've got very slow moving skyrmions, just 1 or 2 meters per second, and there the Hall angle can be almost anything. It's uniformly spread between plus and minus 90 degrees. And so what that means is that these are not moving in any particular direction. And in fact, we interpret this as being, these skyrmions are quite strongly pinned, which is why they don't move very quickly. But also they're moving in directions that are probably imposed by sort of gradients in the local energy landscape. Whereas over here, these skyrmions are in sort of much flatter parts of the energy landscape in the wire. They can move with their sort of proper intrinsic properties. So we've looked at this a little bit more, along with some colleagues in University of Central Lancashire, Sherburn Lepadatu and Callum McKinnon, who've been doing some simulations. They've been using their own code called Boris, which includes both micromagnetics and sort of electron transport properties. And so they've been simulating sort of collective motion, which is when you have a wire full of skyrmions like this. So in the previous case, the skyrmions were sort of far enough apart that you could treat them as kind of isolated individual objects. Here, there's kind of a collective motion. Again, experimentally, we don't see much dependence of the Hall angle on the diameter of the skyrmion. And that is sort of at odds with what you would expect if you only had kind of a spin orbit torque in their model. Whereas on the other hand, they've included another torque contribution, an interfacial spin transfer torque, which has this kind of form and is described in this paper. And what that does is it flattens out this upturn at low diameters. And so there's evidence that this is playing some role actually in this collective motion of the skyrmions. And there's a quantitative difference between the sort of Hall angles we've measured of maybe 10 degrees and this calculated of 30 or 40, and there's reasons to account for that. what we definitely don't see in our data is any kind of upturn here at low diameters. So I want to just finish off talking about electrical detection. Again, these are actually even earlier experiments. And here we had discs where our magnetic material is now just cobalt. We've got 1 micron discs that are connected up with these 4 electrodes in a sort of Hall cross type geometry. And again, it's on a membrane so that we can look at it inside the sticksome. And every time we make a Hall measurement, we can know exactly what the spin texture was that gave rise to that Hall signal. So here are the kind of data that we got. Here there are some images. Actually, you can see this is before some upgrades of the microscope, so they're not quite as clear as some of the more recent ones. But we've got the disk, which has a dark contrast, and there's a patch of brighter contrast here, which is a skyrmion. This is at 0 field, so we've labeled this S equals 1 as 1 skyrmion, so the winding number inside our disk is 1. And as we apply a field, we can compress our skyrmion, and it gets smaller and smaller, and eventually it annihilates somewhere between 50 and 75 milliteslas, and then the skyrmion winding number jumps from 1 to 0 at that point. And so we can see in these graphs as the field is applied, the skyrmion shrinks, the magnetization in the disk rises towards saturation, and the Hall signal drifts down towards saturation. These red lines are the fields at which we're showing images here. And you can do this over repeated field sweeps. Actually, here we did 1, 2, and then 3 up to higher fields to annihilate the skyrmion. So if you take all those data, plot them up like this, well, this is what you see. So on this axis of this plot is the magnetization in the disk, rising from about 0.9 to 1 in these normalized units. This is saturation here. And on this axis, we've got the measured Hall signal, again, normalized to its saturated value, going down here to, in this case, -1 is saturation. We've got this big cloud of points, which we can rebin, and reveals actually, after some averaging, this kind of rather nice linear dependence. So what we're seeing here is as we increase the field, the skyrmion is getting smaller and smaller. So the magnetization in the disk is approaching saturation. The Hall signal is going down, and then just at the point when the skyrmion annihilates and the magnetization reaches saturation, there's this jump in the Hall signal. So this grey line is just a line with a slope of -1, and that's what you would expect if you only had an anomalous Hall effect. So a Hall signal that is proportional to the Z component of the magnetization, which is what we're seeing in the sticksome. Our data sort of lie on this line, which is parallel to that line, but offset from it. So we've got a sort of size-dependent part, which is the slope of the line that's consistent with the anomalous Hall effect. And then we've got this offset, the intercept of this line, which appears to sort of be controlled by the topology, the topological state of the disk. So we did the same thing again. These green points are the ones we just seen, but here for various other disks with other numbers of skyrmions in, -2, 2 and 3, as well as 1. And we always get data sets that kind of lie parallel to this, this grey anomalous Hall only line, but they're offset from it. And if we do the proper averaging and work out what those offsets are and plot them against the number of skyrmions, then we get these red data points here, which are more or less linear. This offset of Hall signal after you've removed the anomalous part is proportional to how many skyrmions we have. It's about 20 nano-ohm centimeters per skyrmion in this case. Now, if we go back to the sort of berry phase physics that I described at the beginning and calculate what you'd expect as a topological Hall resistivity, it's something like 1,000 times smaller. And so you cannot account for this signal, on the basis of this theory. But on the other hand, we're not the only group to have observed these large offsets. There's this paper here from Christos Panagopoulos' group in Singapore. And they also have a more recent one where in that case, they show that it's somehow related to the Skyrmion density. And you can find these large offsets when the Skyrmions are not very dense. I guess what I want to say is that the origin of this is still a little bit mysterious. It certainly can't be explained just on the basis of the straightforward very-phase physics. I just want to finish off in the last couple of minutes by talking about what we've done recently, starting to look at synthetic ferrimagnets, antiferromagnets. So here we have a couple of magnetic layers that are coupled through, say, a ruthenium spacer, so they're antiferromagnetically coupled. And then you can generate a skyrmion in each layer, which will have the opposite winding number, so opposite topological charge. During the lockdown, Elwar Haltz did some simulations, both the sort of analytical and numerical simulations using NUMAX. So what we can see is that these synthetic antiferromagnets should have skyrmions, which are smaller than their ferromagnetic counterparts. They should move faster for a given current drive, and they should also move without any any Skyrmion Hall angle. So these are, potentially interesting things to look at, but tricky to look at when there's no net magnetization in your system. So these are the kind of systems that we've been looking at. So here we've got a couple, in this case, we've got a couple of magnetic layers, cobalt, iron, boron, coupled through ruthenium. There's a little bit of platinum in here, just to make sure we have the same DMI on both layers, and we can get the coupling through that. And here's this region at low field in this polar mote curve where we have the SAF configuration. There's no net magnetization. And when we do a bubble expansion, there's quite a big asymmetry, which shows that we have a strong DMI. And then we've just started to look at these in the stick sum. So in this case, we've got a multi-layer where we've got cobalt, iron, boron, and cobalt, boron alternating. So only every other layer has iron in it, and we can then tune to the cobalt and iron edges to look at the different elements. So here in this multi-layer, we can see at low field, well, this is at 100 Ørsted, so quite a small field. We've got a sort of worm domain structure with maybe a few skyrmions here and there. You can see that again in the iron edge, but not quite so clearly. In these disks, again, we've got these kind of worm domain structures, but it tends to be here on the right-hand side. We've got a few skyrmion-like objects in the disk. And then we made some electrical injectors, similar multi-layer, with a bit more iron in the iron layers, cobalt, iron, boron layers this time, so a bit clearer contrast at the iron edge. And see, here's the Asgrove domain pattern, and you can very clearly see the antiferromagnetic alignment, confirming the SAF structure. And here's a sort of some quite preliminary results, really, where we've been able to use current pulses to create this little patch of dark contrast, skyrmion in the SAF that can be made a bit bigger, and then eventually kind of blows out and fills the whole wire. Okay, so just to conclude, we can nucleate single skyrmions, and we've actually observed that very short, very high temporal resolution. We've observed propagation of our skyrmions through this complex energy landscape, and we can detect them electrically too, and that has two parts. There's a size-dependent part that we can explain with or account for completely with the anomalous Hall effect. Then there's this size-independent part that's somehow related to the topology, which requires some new theory in to understand it. So thanks very much for your attention, and I hope there's some opportunity to answer some of your questions.